in their endorsement, and my team members and I will be presenting about how titanium works as a crystalline structure. But first, I must ask, what do you think aircraft engines, medical implants, and chemical reactors all have in common? Well, they all rely on titanium. And what makes titanium so reliable in these extreme environments is not just the metal itself, but the way its atoms are arranged. The objectives of our presentation are to define titanium as a crystalline metallic solid, to identify its crystal structures, to explain how these structures influence its physical and mechanical properties, and finally, to relate its crystalline nature to its real-life applications. Titanium is a transition metal that is strong, lightweight, and highly resistant to corrosion. These properties make it ideal for demanding applications such as aerospace structure and biomedical implants. What makes titanium especially interesting is that these properties are controlled by its crystal structure. Unlike many metals, titanium can exist in more than one crystalline form, allowing us to clearly see how atomic arrangement affects material behavior.
A crystalline solid is a solid in which atom, ion, or molecules are arranged in a regular and repeating pattern throughout the substance. This repeating arrangement forms a crystal lattice. Because of this orderly structure, crystalline solids have a sharp melting point and well-defined cleavage planes.
Titanium is classified as a crystalline solid because its atoms are arranged in a regular and repeating three-dimensional pattern known as a crystal lattice. This long-range order is a key characteristic of crystalline solids and distinguishes them from amorphous solids which lack a fixed atomic arrangement. In titanium, metallic bonding holds the atoms together in a lattice by a sea of delocalized electrons within this ordered structure.
This table shows the differences between the amorphous solid and crystalline solid. Amorphous solid lack an ordered structure and their particles are randomly arranged. They soften over a range of temperature and do not have definite cleavage pattern. In contrast, crystalline solids have a regular structure, a sharp melting point, and distinct cleavage plane. Examples of amorphous solids include glass and rubber, while crystalline solids include diamond, salt, and quartz. Crystal lattice is the regular three-dimensional arrangement of a particle in crystalline solid, while unit cell is the smallest repeating structure unit of the lattice. When the unit cell is repeated in all directions, it forms entire crystal lattice. The unit cell is microscopic, while the crystal lattice is macroscopic. Metallic bonding is the force that holds atoms together in a metallic substance. In metals, atoms are closely packed and their outermost electron shells overlap. As a result, valence electrons become delocalized and can move freely throughout the metal lattice. This explains why metals are a good conductor of heat and electricity.
Hi, I am Farah Atika and I'm going to explain about crystal structure of titanium. There are two crystal structures of titanium. The first one is alpha titanium, also we call as hexagonal closed pack, in short HCP. And the second crystal structure is beta titanium, which we call body-centered cuboid, in short, BCC. Next, I'm going to tell you about structural differences due to temperature on HCP and BCC. First, HCP at room temperature up to about 882 Celsius, titanium exists as alpha titanium. Alpha titanium has a hexagonal close-packed structure, or HCP. In this structure, atoms are packed in a repeating hexagonal pattern, which give high packing efficiency and strong atomic bonding. Because of this tight atomic arrangement, alpha titanium is strong and stable, which makes it suitable for applications that require high strength at normal temperatures. Moving on, when the temperature increases above approximately 882 Celsius, titanium undergoes a phase transformation. The crystal structure changes from HCP to body-centered cubic, known as beta titanium, or BCC. In the BCC structure, each unit cell has one atom at the center and atoms at the corners. This arrangement is less closely packed compared to HCP but allows greater atomic mobility at high temperatures. Moving on, this phase transformation is reversible and is driven by temperature. As thermal energy increases, atoms gain enough energy to rearrange themselves into a different crystal structure that is more stable at higher temperatures. In summary, titanium HCP structures at low temperatures provides strength and stability, while its BCC structure at high temperatures allow greater flexibility during processing. This structural change is very important because it directly influences how titanium behaves during manufacturing and use.
Next is deformation mechanism. This is how deformation happens in metals. Plastic deformation occurs when layers of atoms slide over each other along specific planes called slip systems. Deformations become easier when atoms are closely packed and when there are many slip systems available. When stress is applied, bonds break only at certain points, allowing atoms to move without breaking the entire crystal structure. Why structure affect mechanical response? The crystal structure determines how closely atoms are packed and the number of orientation of slip system. Materials with high packing efficiency and many slip systems deform more easily, making them more ductile. On the other hand, structures with fewer slip systems resist deformations and are more likely to fracture, which make them brittle.
This system in crystal consists of slip plane and the slip direction. Both are densely packed. For HCP titanium, it has limited slip system, mainly basal slip. Because slip is very directional, atomic movement is restricted. As a result, it has a lower ductility at a room temperature and is difficult to cool work. Next, for BCC titanium, there are more potential slip systems. At high temperature, atomic vibration increase and active more slip system. This leads to higher ductility and better formality.
This is why titanium is often processed hot. At high temperature, titanium transforms or behaves like BCC. More active slip system reduce resistance to deformation. Hot processing will prevent cracking, allow shaping and fogging, also improve mechanical uniformity.
Continue to the differences between HCP titanium and BCC titanium. First of all, we have crystal structure. For HCP titanium, it is in HCP structure, while for BCC titanium, it is in BCC structure. At room temperature, HCP is stable at room temperature, while for BCC, is stable above 882 degrees Celsius. Next, phase name. For HCP, it is alpha titanium, while for BCC, beta titanium. Number 4, slip system. HCP has limited number, while for BCC, many slip system active at high temperature. Strength for HCP, high strength, and for BCC, lower than A titanium. Ductility, HCP has limited ductility, while for BCC titanium, it has high ductility. Formability, poor at room temperature for HCP, and excellent at high temperature for BCC titanium. and anisotropy. HCP has high anisotropy, while for BCC titanium, more isotropy. Ease of deformation, difficult for HCP titanium, but easy to hot work in BCC titanium. Manufacturing significance, used for high strength application for HCP, while for BCC, used during hot working farming.
Now I'm going to talk about applications of titanium. Titanium, especially titanium alloy, usually used in many fields such as automobile, medical, and in our daily life, as it has low density, good corrosion resistance, and non-toxic to us humans. Applications of titanium in automobile industry. Reducing fuel consumption is one of the main mission in automotive industry. Since titanium is known for its low density, the body of the car is now lighter and fuel consumption can be saved. Next is applications of titanium in medical fields. Titanium is also used in surgical instruments, prosthetics, and even surgical implants. As it is non-toxic, titanium are widely used as bone implants on human body because it is surprisingly compatible with our cell. Last but not least, applications of titanium in daily life. We can say that titanium is a part of our life as it is mostly used in spectacles, jewelries, and sports equipment since it has low tendency to corrode, which makes it longer usage life. What we can conclude is that titanium is a crystalline solid in which its atoms are arranged in a highly ordered and repeating lattice structure. At room temperature, titanium exists in a hexagonal closed-packed HCP crystal structure, which gives it high strength, good mechanical stability, and resistant to deformation. Overall, the crystalline nature of titanium is responsible for its valuable physical and mechanical properties, making it widely used in aerospace, medical, and industrial applications.